Hello all! So, in spite of everything, I am still your TA. We still have Chem 116 to do, and we still have labs and things like that to do. Now, I know that this is the first time that a lot of you have done online instruction, especially on such a large scale. So a lot of you are still catching up on all the tips and tricks of how to do that, as well as how to learn from home. So I'm going to try and make sure that these videos specifically are always available to you at all times. By that I mean that I'm going to upload them onto YouTube and also onto your Blackboard page. So you will always be able to access them. There's not going to be a time limit on them. I have a few instructors who've put time limits on their videos, and I feel like it's a bit stressful, especially if you have a very busy week or a week where you just don't want to do school because you need a break from sitting at your computer. In which case, these are going to be available to you at all times. I wanted to point out that my office hours are now changed, in a sense. I still have my normal one on Tuesdays at 11:30, but I also have an extra one on Thursdays at 7:30 p.m., and this is specifically for people who want to start their homework, which I would definitely do, people who are having some trouble with the lab report in general, and again, just for any general questions, because I definitely want to be able to help you, be that listening ear, and also make sure that this is as smooth a transition as it can be. Now, I also wanted to point out that my email is posted here, and these slides will also be posted onto your Blackboard page, so you will be able to see them and be able to access this information. But specifically, I wanted to point out that my email policy, which is that I will respond within 24 hours, has been switched to 12 hours. And that means that I will always respond within 12 hours. People who have emailed me before will know that I do respond well before that. I try to respond as soon as you do send me an email. But because I also have moved everything online, I will be online, but I might not see your email, or I might be doing other things online. So do know that I'm going to try my best to get to you as soon as possible. So that being said, this is technically week 11, but it's also week 1 of online teaching. And just send me anything you want that we can fill these slides with. They can be things that homework have gone wrong, things in the lab that are confusing, things in the pre-lab quiz that didn't go well. I want to go through all those things with you. So please email me about those things, because otherwise I won't always know how to fill the space. All right. So acid-base equilibria, some things that I feel like need to be highlighted is that Ka is for acids and Kb is for bases, and specifically the dissociation of those acids and bases, and therefore a product of your Ka value will always be the hydronium ion, aka H3O+, or it's going to be the hydrogen proton ion, which is H+. And then for Kb, a product will always be OH-, that hydroxide ion, and that's going to be in the numerator, the top row, when you're setting up your equilibrium, because again, those K values, as much as they are dissociation constants, are also the equilibrium, that dissociation equilibrium of the acid or of the base, depending on A or B. So just keep that in mind, and also means that ice tables are still a thing, because we are working with equilibrium in terms of those concentrations. So I know a lot of you don't love ice tables, but they are definitely going to be a large part of your exam, your final exam, as well as this next exam. So please, if you're not sure about them now, email me so we can go through them, maybe set up a private session to go through them, etc. I've done that with a few people in the past, and they said that was really helpful, so please feel free to utilize that. All right, another thing that someone said to me is that I got a few emails about when can you ignore X? When is X negligible? And I wanted to highlight that it's the 5% rule. So what I mean by that is it's the math way to determine whether X is ignored. And what I mean by that is if you have X, which is your change value, that X in change, either negative or positive, in this case we ignore the negatives, and you divide that by the initial concentration, so that's going to be what they give you. So if it's a product per se, well, the initial concentration is 0, and then we have an imaginary number, in which case you would then assume that it can't be ignored. But other than that, usually you will be given something for a reactant. You're going to take X divided by your initial concentration of your reactant. And if that is less than 5%, then you can ignore X. So an example I wanted to give you is that the initial concentration was 0.25. 5% of that is 0.0125, but the X had a value of 0.0095, which is less than the 0.0125, and therefore we can ignore X. Okay? All right. So this lab is in 3 parts. The first part is a strong base and a strong acid. So you're gonna have your volume of titrant added will be your NaOH up here, and then you're gonna have your HCl with an indicator in the bottom. So the indicator is clear when it's in an acidic solution, aka HCl, and then when it gets into a basic solution, it turns pink. So that's why when you start adding NaOH, when you start seeing that pink color, it means it's slightly turning acidic. And so we wait until it turns pink very faintly, and that's when you've just reached past the equilibrium point, but we always assume that that's basically equilibrium. Because we won't actually be able to see the equivalence point. We'll only be able to see just past it if we're really good at it. Now, I wanted to point out that you're also doing a strong base with a weak acid, aka acetic acid, which is in your vinegar. A bunch of different vinegars that you would have tested. But in this case, the difference between this graph and this graph is specifically of this buffering zone. And the buffering zone is where you have a strong base that is literally fighting against this weak acid. So while there is a lot of weak acid, it already is trying to jump in pH into the basic range, and that is because it's such a strong base that's completely dissociating. So it's very quickly taking up those H+ ions. That's the difference between this graph and this graph. Now, then you're going to do calculations, and basically the calculations are mostly your calculus stuff, and if you haven't done calculus, then it's simply taking the first derivative, and that maximum is then going to show basically where it crosses in your second derivative at 0, and that's going to be the volume at which you get your equivalence point, because that 0 corresponds to the 0 slope that we get at equivalence. So that's kind of how those relate. So that's why this is at 0. And that's why we also take it at the max, because at the max, the tangent to that max is 0. But again, we don't see the first derivative, so I'm not going to go too into detail about that and not too into detail about the calculus. Just know that that is why we get those numbers and why we take those derivatives. All right, so something I wanted to highlight really quickly is the titration of a strong acid is very different from the titration of a weak acid in a few very big ways. So one, you're going to notice the titration of the strong acid versus a strong base has an equivalence point at about a pH of 7. This makes sense to us because a strong acid very much is going to have its moles of the titrant, aka the strong base, is going to equal the moles of the strong acid, which is going to probably be at about the equivalence point of 7. However, with a weak acid, we're going to find that the equivalence point happens at a higher pH, and that's because this is a strong base, which means it's completely dissociating, while this weak acid is not. And so that means that the equivalence point will come much later. Now, this can be a bit different, and I'm going to pull up my pen. Now, say that we have this is actually going to be a strong base. So instead, I have a base here. We're going to say that this is going to be our NaOH, and we're going to say that this down here is going to be HCl, because HCl is always a very common strong acid because its pH is that of 1. So this is now HCl. If that were the case, then we would start at a very high pH that would then slowly come down, reach equivalence point, and then it'd come back out this way. Sorry my line is so messy, but that's how that went. But as you can see, we still get this region here where the equivalence point is at 7. Now this is a bit different when we're working with weak acids and weak bases, and the reason that this is different is because that equivalence point is actually going to happen in a more acidic pH, and the reason for that being is similar to the reason before, but in this case the HCl, remember, is now completely dissociating, and that HCl means that the equivalence point is going to happen at a more acidic pH because we now have more of a dissociated acid in comparison to base. And so what you're going to see happen, I'm going to start at a bit of a lower pH because again we're now a weak base, is that you're going to come down and then you're going to see this equivalence point drop and then it's going to come out like this. Cool. So you see that this is now occurring at a lower pH. We'll say pH of like 4 or something here. And that is the reason being is that, again, we now have a strong acid that is completely dissociating HCl in comparison to a weak base that is not completely dissociating. So that is how these relate to each other. And please know that you can go vice versa on that. Okay, so going a bit more into detail, just kind of explaining what half equivalence is. So the word half equivalence actually comes from halfway between the origin and that equivalence point that happens. So that's why it's called half equivalence. And what's great about it is it's when the pKa equals the pH. So that's when we have our dissociation happening that's equal to that of the hydronium ions, which is what happens at half equivalence, because that's when you have about half of your hydronium ions are there, and also that's because half of your acid has dissociated. Whether it be a weak base versus a strong acid reaction, or whether it's a weak acid and a strong base reaction. And then the equivalence point is when there is an equal number of moles of titrant to the moles of the solution with an unknown concentration. So that's why it's the equivalence. That's when those two things are equal. So when the moles of the acid equal the moles of the base. All right. Now, this can differ though, remember, because with weak acids and strong bases and vice versa, you're going to have varying volumes. So remember that you do need to be very confident in the fact of going from molarity to moles with different volumes. That is a underlying calculation that you should be very comfortable with before you endeavor in all of your calculations. Okay, so we're going to go through a problem here. Now, here's some good things to note. So we got HCl, this is a strong acid, and that means it's going to completely dissociate. And then we got NaOH, and NaOH is definitely a strong base, and that also means it's going to completely dissociate. So when we think about what we're going to do, we are going to know that the given concentration of HCl equals the concentration of H+, and then the concentration of NaOH equals that of OH-. That's what we've known from before. But I'm going to tell you that you have to remember that in this case, we're looking at the H3O+ is equal to the moles of H+ over the total volume. And a lot of you would quickly plug in 0.01 then for your moles of H after doing 0.1 divided by 0.025 to get the number of moles. But I would tell you that that's wrong, and the reason being is that this here is not exactly that, because remember, we've just added in a bunch of base. And so what's actually going to happen is you're going to get the moles of H3O+ from HCl, subtract the moles of OH- from NaOH because they've been neutralized by that HCl. So just keep that in mind. And then we're going to take this and this information, and when we get the 25 mils of the 0.1, remember your mils does need to be converted into liters. So then you're going to take 0.1 times 0.025 liters to get 0.0025 moles, and you're going to do the same for your NaOH, and what do you know, they're the same. So we kind of remember back, and I kind of hinted at this, but they're kind of equal, which would kind of assume that the pH of these two is neutralized at 7, but we're going to show why that is mathematically. So what happens here is that your H3O+ equals the moles of H+, which the way that we've defined the moles of H+ is 0.0025 minus 0.0025, which is 0. So 0 over 50 is 0, so there's a 0 concentration, but we know the negative log of 0 is 1, and that makes no sense. So we're going to do this through, and we realize, okay, if our concentration of H+ is equal to that of O-, then we know that we're working with water, and we're going to involve the Kw equals Ka times Kb, in which case our hydronium concentration would be 1.0 times 10 to the minus 7. Again, we plug that into this lovely equation here. We plug in our 1.017 into here, and then we get pH of 7. So this is when it's neutralized. Same as what we saw in our graph. So it is akin to what we saw in our graph before. Great. All right, but what if they weren't at equilibrium? And this is something that a lot of you are going to encounter on the exam, so I kind of wanted to highlight it. I'm just pulling up my notes. And so what happens if instead we've added 12.5? 12.5 of the strong base. Now let's look back to our graph. There we go, not that graph. This graph. So here, so instead of adding 25 mils and getting to our equivalence point, we've instead added 12.5. So we should expect an acidic pH, something around between 1 and 2. This is something that I'm going to ask you to do in the exam as well, to kind of do a common sense check.
in that when you have a strong base and a strong acid, if you know that 25 mils is how much you need to neutralize the entire solution, then if you're adding less than that, you should expect an acidic pH. If you add more than that, you should expect a basic pH. The same with your weak acids and your strong bases, or vice versa. Find your equivalence point, and then when it shows you how much you've added more than that or less than that, you'll accept the following. So in this case, less would be something acidic, and then more would be very basic. All right, moving forward. Okay, so this way I'm going to do it the same way I did last time. There we go. So I'm going to use the same idea, moles of H+, except this time the number of moles of NaOH has changed. So it's 0.1 times 0.0125 liters, and also my total volume has changed. That's the other thing that people usually mistake. Remember that your total volume is also changing. Sometimes we don't do that because when we're going through our calculations, it doesn't make sense. But do remember that your total volume is also changing, as well as your moles when you're moving around your volumes. So then we do the math, and we get 0.033 moles, or molarity. And then we plug that concentration into our lovely equation here, and we get 1.477. If you remember back to our graph, you're going to realize, that's what we said, about a pH between 1 and 2. And this makes sense to us because we've added less base than how much we needed for equivalence. For equivalence, we needed 25 milliliters, but in this case, we've added less than that, literally half. And so it would make sense then that our pH would be more acidic, because at this point, since these have the same molarity, and therefore we can say the same amounts, we have now more acid than base. Now the reason I can compare them this way is because they have the same molarity. If they had different molarities, I wouldn't be able to make such a direct comparison. But that's why I chose this example, so I can show you that literally we have more strong acid than base, and therefore that's why we have a more acidic pH. But do know that that's not always true if the molarities are different. Okay. Now, you're working with acetic acid, and acetic acid is actually a weak acid, and we're going to be doing it with a strong base. And so one thing that we're going to have to do is find the initial pH before we've added any of this base. And so the first thing we're going to look at is the Ka, because this is a dissociation constant. And the Ka is going to have, again, like we said before, hydronium ion in the concentration right here in the product line, and then the conjugate base all over the acid, aka H, A- over HA. This is something that we should be really familiar with. Now this is actually going to be not that bad. So if we don't have any base, then this is quite easy. This means that we have Ka equals the hydronium ion squared over the initial concentration of acetic acid. And that's because we have no conjugate base. We haven't added any base to make the conjugate base and to extract that H+ ion off, and therefore we just have the hydronium ion squared. All right, so if I rearrange this, because again, remember I'm looking for the pH, which means I'm basically trying to get this concentration of my H3O+ alone. So then I'm going to take the square root, and now I have my H3O+. I'm going to look here, and I've got Ka and the initial concentration of acetic acid, and what do you know? That's given to us in the problem. So I got my initial concentration of my acetic acid, and I have my Ka value. So I'm going to plug those into here, and I'm going to get this lovely equation here where I have my Ka value multiplied by my concentration of my acetic acid, and then I get the concentration of hydronium ions. Perfect. And then I'm going to plug that into this equation, and I get a pH of 2.87. So that's the initial pH. I would say, as a general rule of thumb, anything with a pH of 3 to up to 6 is a weak acid. Anything from a pH of 12 to a pH of 8 is a weak base. Anything 13, 14, sometimes 12 is considered a strong base. Sometimes, so that one's kind of iffy, but usually they will make it very clear to you whether it's weak or strong. They'll give you a very clear pH. But in general, for acids, it's pretty clear that anything that's 3 to 6 is definitely a weak acid. So that's kind of the idea. All right. So now we need to find the pH after we've added 25 mils of that 0.1 molar. Now remember, 25 mils is how much it took to neutralize the HCl. But we would know that this would not be enough, or sorry, this would not be the equivalent, this would not mean that the pH is 7 at the equivalence point for this exact problem. And the reason we know that is because we're working with a weak acid now and not a strong acid. So things are not completely dissociated like they were before. So we look at this and we say, okay, we know that the equation's a bit different because we have all of the acetic acid becoming its conjugate base. Then, if I know that, that means that this concentration is going to be equal to that of my conjugate base anion that we have up here. Perfect. All right, so if I calculate this out, I'm going to get my concentration of my acetic acid conjugate base, which is 0.05 molar. Perfect. Now that I've done that, I'm going to need to think about Kb. Kb, I'm going to get from this equation up here. Again, Kb is going to have that OH minus anion in the numerator multiplied by the acid all over the conjugate base, aka this is B, and this is HB, and this is our OH minus. All right, the other thing Kb equals is Kw over Ka. And luckily, we do have those values from up here. I have my Ka value, and I also have Kw, I know from the equation. So that gets me 5.6 times 10 to the minus 10. So I know what Kb equals. Then I know that these are X. I have no idea what they are. And I do know the concentration of my conjugate base because it's the same as my concentration of my NaOH minus here. Now, someone asked me this before, and I wanted to highlight this OH minus is not this. Like I said before, you are adding this NaOH to the acetic acid. So that concentration of NaOH is no longer applicable to the solution you've made because this solution is a mixture of NaOH and the acetic acid. And that OH minus ion is now being convoluted with other ions. So we cannot just directly assume them anymore. So this is not going to equal this concentration anymore. They will be different. This, however, does equate to the conjugate base because they are directly related in a 1-to-1 mole ratio, and because this is a product, or sorry, is a reactant that goes into Kb that we get from this only. If you think about an ice table, there's 0 of this to begin with, and then we add this many OH minus ions to it, so we're adding that molarity, in this case, this molarity here, to the equation. So it's like in your ice table having 0 plus 0.05. If I've lost you on that, let me know, and we'll fix it. But that is the reason. So if you were to drop an ice table, you would see that these are both X. There's 0 of these there's 0 plus X of these, and then there's 0.5 because from a previous ice table before we did the Kb ice table, which I know sounds very confusing, you would get that if you had NaOH with your acetic acid, you would get that these deplete to 0, and instead you get the acetic acid conjugate base as X equaling 0.05. Anyway, moving forward with the question at hand, we then set our Kb value equal to X squared over 0.05 molar, which then equals 5.3 times 10 to the minus 6. Again, this is Kb, so that means we're doing pOH. Please don't get confused, and remember what you're solving for is pH. You will get tripped up. They will put in an exam. The pH equals your pOH value, and you'll think, oh, that's it, because I've got it, I see it, it's the same. But really, you've gotten pOH, but after doing all this work, you're going to forget that you've solved for pOH. It happens all the time. I do it all the time. That's why I'm warning you, don't let you do it in this exam. So I'm going to plug in my OH minus, my OH minus concentration X into the equation. I get the negative log, which equals 5.28. So pOH equals 14 minus pH, which means pH equals 14 minus 5.28, which equals 8.72. Again, all the way back to our graph. That's exactly what we saw in our graph. If I get there. Nope, a little bit further, more. There. Our equivalence point was at 8.72, and that makes sense to us because if we do a reality check, you're like, okay, weak acid. Weak acid does not completely dissociate, but that means I'm going to have to add a lot of hydroxide ions to be able to abstract those H's and be able to then give us the equivalence point, which means it's going to come at a higher pH. Because again, that weak acid needs a lot of power to dissociate. So that's the reasoning behind that. So, hope that makes sense in a way. Let me know if it doesn't. Let me know if you need any help with this lab report. I know it's very weird because you've been given all the data. They are going to post or have already posted a video of me doing it actually with a few other really wonderful TAs. So please go check that out. It does kind of make a bit more sense and we give a bit of hints about what to do. And as well, in case you're not comfortable with calculus, let me know. I'm not comfortable with calculus, but I can definitely give it a whack. I do know this calculus for the very reason that I've done titrations before, but other than that, I'm as clueless as the rest of us. And let me know if the 5% rule makes sense to you all. The 5% rule is not a hard and fast rule, but it is a well-used rule. Most people use this rule, and almost everything applies to this rule, and the things that you will encounter in the exam will apply to this rule. So don't worry. This is generally what's accepted. All right. I hope you guys enjoyed this. I hope this was helpful. Please let me know your feedback. Let me know what you think. Let me know if you want different videos, if you want the focus to be on different things, what you would like to see, and I will take all that on board because I don't know what's helpful at this point for you guys and what isn't, but I'd love to know. So please let me know and I will make it so. All right. I hope you guys have a wonderful week, and I hope to see some of you on Thursday during my office hour. Okay. Bye for now.